Hello, everyone. I know it's the last talk of the day, so let's try to make it a little bit of fun so you guys can go have some drinks in New York City or whatever it is you do for fun on a Wednesday night. My name is Ivan. I'm from Pure Storage. A lot of people ask, who's Pure Storage? We are obviously a storage company. We build storage products that go inside of your data centers. I am a software engineer. I'm the tech lead for our big data analytics team inside of Pure Storage. We build solutions to process logs at scale. We generate large amounts of logs internally as well as externally. We have a lot of our products, like tens of thousands of our products out in the field, and these products generate massive amounts of data. You can think of all of these products as sensor networks. Additionally, we also have a lot of our products internally that we use to test and do during the software development cycle. So I'm going to be covering how do we do log analysis at scale, and essentially the architectural thinking and all of the takeaways that we've learned after doing this project for now about a year and a half. So I know I'm going to lose your attention fairly quickly. So before I do that, let me give you some numbers just to try to capture a little bit longer of your attention. So we have a log analytics pipeline, and in terms of numbers, the streaming pipeline is processing 1.5 to 2 million events per second. The SLAs for log events is 5 seconds. So from the moment it comes in, it's being generated until it's ready to be processed or alerted, or the different actions that we support is 5 seconds. And in addition, we also are processing about 0.5 to 1 petabyte of data per day. That's outside of the streaming. All this data that is being streamed is also being stored. And a lot of times we have to go back in time and look through data that's been stored. And that's what's that 0.5 to 1 petabyte of data per day. So let me cover the use case for log analysis inside of Pure Storage. The biggest use case and our biggest need was our continuous integration and continuous deployment pipeline. For those of you who don't know what continuous integration and continuous deployment is the process from where on the left-hand side you have developers, and on the right-hand side you have products and code that you ship. And it's the process of automating that pipeline from writing code until you ship it. The first, obviously, you're touching the source, you're making changes, you build it, or also people call it compile it. You do some functional level testing, try to test unit tests, maybe testing some of your subsystems. Then you do stress tests, you scale your systems, you push it into like the real world workflows that you're doing. And then you eventually, if it passes all of those tests, you can just deploy that code automatically. Inside of Pure Storage, functional testing and stress testing happens a lot. We do heavy automated testing, and it generates a lot of log data. And we've always invested in CI/CD, continuous integration, continuous deployment, from very early on of the development of our products. So when we started, it was a small team, right? We were a startup in Silicon Valley so many years ago. We're under 10 developers building a storage product. We had less than 5 of our prototypes, right? You can imagine you're building hardware, so you prototype it rather quickly, a bunch of tape on a lot of the parts. And we had some servers that are generating the load that are pretending to put stress on our storage systems. We use Jenkins as a testing coordinator, for those of you who are not familiar with. We would run about 200 to 300 tests per day. And that allowed us to catch bugs really quickly, right? There's less than 10 of us, but one of us introduced a bug. A test would fail, and it was very simple. It would just send you an email to the last person that touched the code. And when there's under 10 people, that works really well, right? Because even if you didn't touch it, you still know everything about the system. You can probably triage it and debug the problem, figure out what's wrong. Fast forward about 2.5 years. Lucky for us, we're no longer a startup. We're a mid-sized company now. We have, in this particular product, we have over 100 software engineers. We now have this is at the time when this project was starting. We had over 250 of our products in the lab that are constantly 24/7 running tests and generating logs and passing or failing these tests. These products are actually expensive. You can't just get a ton of them to test. So even though we wanted to scale the number of products with the number of engineers, we couldn't, financially speaking. So we spent some development time to build simulators of our product. So we simulate our hardware in software, so we can run essentially as many as we want with just normal servers. So this is what these VMs right here are. At the time when we started, we had about 1,500 of these VMs, and they would simulate our hardware, and we could run functional level testing. We couldn't do stress testing, but the functional level testing would work just fine. We have about 700 clients that they're pretending to be our customers that are putting the stress on these different systems, whether simulators or our hardware product, which is called the FlashArray. And at the time, we already had about 20 different branches. Some of them release branches, some of them feature branches, and each one of them needed to have its own orchestration system for the testing part. So we use multiple instances of Jenkins. If you're familiar with Jenkins, it unfortunately doesn't scale very well, so we just spread out that way, a Jenkins per instance. And at this point, we were running about 70,000 tests per day. Now, that number may not sound like very much, but if you're familiar with software development and software developers, we create bugs all the time. No matter how good you think you are, you're going to write bugs. And no matter how good your unit testing is, you're going to write bugs. So a 1% failure test rate of your test, it is normal. And it is actually fairly common. You'll find a lot of software development shops, they'll have 5% failure tests, and they speak very proudly of that. So you have 700 failures. Now, each of these failures, 1%, right? Very, very conservative. Each of these failures takes about 15 minutes to triage. Why does it take so long? Right? We're testing a hardware product. The hardware product is connected via the network. The hardware product itself is a distributed system, so it has at least 30 different components. There are about 10 different software packages that we've written ourselves that are in these components. And then we still have the testing framework that we've written. We have the actual connections between the clients. So there's a lot of different places where stuff can go wrong. So for an engineer to go figure out why did this, say, read operation of a storage file system fail, they have to go through many, many layers of logs to understand what happened. So that's why it can take at least 15 minutes to triage one of these failures to understand what part of the system failed. Was it the network? Was it one subsystem? And then they can assign it to the right engineer so the engineer can go look at it. Now, if you multiply 700 failures with 15 minutes, you quickly realize that you need 20 full-time people that are working 8 hours a day doing nothing but looking at failures. Our team had 100 people, 20%. Too expensive, we said. Too many people. In a lot of places, that's normal. You'll find that 100 engineers will have about 30% of QA. But we wanted to do better. So we said, can we do better? Especially because we knew all of this was going to grow 2x in the next 12 months. So can we build a log analysis system that can help us solve some of these problems and lower the load on these engineers so we can use as few engineers as possible? And the first thing that we realized is that, yeah, you might have 700 failures, but you don't have 700 bugs, right? I mean, if you do, I'm so sorry. But you don't have 700 bugs. The reality is you probably have, I don't know, somewhere between 10 and 50 bugs. Some of them are bugs that you know and you're happy to live with because you know they're just testing bugs and they may take a really, really complicated effort to fix, but you know they're not problems, so you want to automatically find those. A lot of those other ones are going to be bugs that they're so complicated in a very particular subsystem that they have a lot of different symptoms and fail a lot of different kinds of tests. So what you end up having is triage engineers that are going down through the logs, spending 15, 30 minutes, 45 minutes, and then at the end of the day, it's like, oh, it's the same bug that I just triaged yesterday, right? What a waste of time. So we wanted to optimize that. So our dream was to automate the triaging of failures as much as possible. Try to remove all the repeatability from the human process. We figured that's a low-hanging fruit. And we said, well, what else could we want, right? The logs also have a lot of performance data. We're writing a lot of human-readable performance data from all of our different subsystems, and we wanted to extract that and process that automatically. Everyone does that. It's called ETL. Take the unstructured data, convert it in a way that you can aggregate it, search it, do a bunch of these different things. We obviously wanted to save our logs for future use. We are selling hardware, which means that a year down the line, one of our customers could come back to us and hit a really, really nasty bug, what is called a day zero bug. And you're going to want to go back in time since you created this hardware, and try to find the similar patterns to see if this is something you've seen before. This is very important for us. Hardware is really hard to get right, so we wanted to save those logs for future use. We also wanted to obviously do this in a scalable system because, as I said, at the time we had plans to grow 2x in the next 12 months, and we're still on track for that. And obviously real-time results. When a test fails, you want to shorten the time until you can automatically triage it or not. So now let's take a step back. So this is the problem that we were faced inside of Pure Storage Engineer. And let's take a step back on how we looked at log analysis in general. And whether this is a line or an exponential curve is up to you. But essentially, you classify logs in terms of volume and value. You're going to have on the left the logs that are the lines that are going to be super spammy. Honestly, some developer just added a line, they wanted to debug it, they don't really realize how much cost there is to that. You can't control developers, right? So you're going to have spammy data that, yeah, maybe you need it for that one time that you're going to debug something, but most of the time you don't need it. And on the right, you have those errors that happen once in a million times, and you want to capture them and alert somebody as soon as they happen, right? So first is you can think of, well, we want to save all the logs, but there's that tiny little thing on the right that we want to alert or take action on. Second, you have certain part of your logs that actually have structure, or they should have structure, but you chose not to add structure because you wanted them to be human readable, like everyone else. And so you want to ETL those. You want to extract that data, the numbers that are in there, add some structure, and put them into a database that allows you to look at, in our case, performance analysis over time of how our software is doing. Last one is the kind of data that you want to aggregate and search. These are, for example, all of the warnings in the logs, right? When something goes wrong, you want to go look at all of the warnings that are happening for a particular host, for a particular test, the different slicing and dicing of the data. And if you're building a log analysis system and you're successful, you have to plan that maybe when you start, this is the breakdown of your logs, but maybe a year down the line, this will be the breakdown of your logs. So you have to think about the subsystems that you're going to build and how you're going to scale the different parts of your pipeline that are processing the log and sending it to different use cases so that you can support this. Each of your subsystems should be able to alert on every single log line. So that way, no matter what happens in the future, you're ready, right? So the architecture tries to take that into account. So how do we architect this, right? And again, before we start talking about technologies, let's talk about conceptually. Always on the left, log sources. In our case, I talked about VMs, network. Our product was called FlashArray, a bunch of different software pieces. For you, it might be your web application or whatever it is that you're doing. Everyone wants centralized logging, which is essentially what we're getting by storing all of our data. You tag the data as it's coming in. You write, what time was this data created and where is it coming from? You're making it semi-structured data, and you're centralizing. You're writing it in a single place that's going to be the source of truth for all of your logs. And obviously, you got to store that. On the right-hand side, you have the consumers of the data. Whether I mention aggregation, transformation, you want logic for alerting for those once in a million kind of errors. So you need efficient access for these applications and services that you have on the right-hand side, whether, again, aggregation, transformation, and logic, from all the data that is coming in. So what does that mean? You have to create an index. You have to create an efficient way for these services on the right to query the data that is coming in. Now, as I told you, when you're starting, less than 1% of your logs are actually going to make it to these services because you're just starting to figure out what is useful from these logs. So why are you paying to index 100% of your data if you're really only using 0.01, which was the case in our world? And indexing is a really expensive operation. It takes a lot of compute power to churn through all of the log lines and slice it and dice it in a lot of different ways so you can search it quickly. So if you don't want to index everything and you kind of are figuring out what to do, the obvious step is, well, let's add a filter step, right? I know what I'm consuming on the right, so why don't I add a filter step before I index and only index stuff that I know I need? And you obviously need a streaming buffer there because, as you know, filtering, it's at the end of the day software, it can crash, and you want to be able to smooth the line out of, data doesn't come at 2 million events every single second. So 1 second is 2 million, the other second is 1.2, and so you want to average that out so you have enough compute to handle that at a full peak. And the question that you're going to ask me is okay, maybe you're indexing all the data that you think you're going to need today, but what about the data that you don't know you need, right? You're still going to have questions to ask of your data tomorrow that you cannot filter on today because you don't know what that data is. And that takes us to the last step, which means you need a way to refilter the data, right? So conceptually, our architecture allows us to do all of these steps. And when in the past, all your storage had to do was obviously just be able to keep up with the writes, asynchronous append to a lot of files. And now you need to refilter, which means you need now also high throughput on the storage. And that puts obviously limitations on what kind of storage you can use. Something like S3 in the cloud would be probably a good alternative, right? And now let's break these little boxes that I've defined here into technologies. In our case, we use our syslog for the augmentation and centralization of the data. all of our data can essentially be piped through syslog. Already, a lot of our systems were writing to the local disks in their own host through syslog. So adding remote rules so that that data gets also streamed off of the host, whether it's, again, a compute machine or a FlashArray or whatever the different sources are. You can just tag that with the source name, the host name, the timestamp, and send that data over through the network TCP. You have a remote set of our syslog servers. All they do is they, again, add that metadata and store it. Store, in case it wasn't clear, we have to use our own products. I mean, we don't have to, but it's really cool to use them and showcase what they can do with them. This is the FlashArray product. Again, it's a network-attached system. Essentially, NFS, for those of you that are familiar with, which is Network File System, or an S3, just like in the cloud, an object interface. So we use, in this case, NFS, because we need the append operations. We can't use S3 for that. So we're constantly just appending to files. And we are saving all this data in a semi-structured format. And I'll get into the format a little bit later so that you understand the kind of queries that we do with that data. But here, we're storing 100% of the data. As it's coming in, it's just the first thing you want to do is make sure you have it. Persist it, because you cannot recover that data. On the filter stuff, we need a streaming buffer, and everyone knows that Kafka is probably the most popular thing. It's really easy to scale. It doesn't consume a lot of CPU. It's really essentially simple to monitor, very, very straightforward to plug in. And Kafka, again, smooths out the operations that we do from the streaming side to the filter step. Now, the filter step is taking essentially, we're using Spark streaming for the top part and Spark batch for the bottom part. It's consuming from Kafka from the streaming side, and this filter step essentially takes a long list of configurations, which are all the patterns that you care about today. Those long lists of configurations happens to be JSON. It's imported through our own little system that people can insert the patterns that they want to filter, or you can think of as the kind of log lines that you want to subscribe to. Right? So certain services will subscribe to certain log lines. Developers choose to subscribe to certain log lines. And Spark, again, same code that runs on the Spark streaming side as well as on the Spark batch side. It's very simple. The only thing that changed is where's the data coming from? Is it coming from Kafka or is it coming from FlashArray, which is just a file system? Now, the interesting part, and the part that was as surprising to us as it is to a lot of people, is that for an indexing, we started when we first did this project, we started with Elasticsearch. And you can think of any kind of database to build an index, right? You can use SQL, you can use Elasticsearch, you can use Splunk for logs. And we always thought from day one that every single part of the subsystem needs to be able to take every single line. So when you have that kind of scalability in mind, and we knew we're growing to essentially 5 million events per second, to be able to ingest that much data, 5 million events a second, is you're talking about 100 terabytes of data per day. Our average size of a data is somewhere between 400 and 500 bytes. Elasticsearch just becomes really, really expensive, right? It's a lot of CPU. So we went with indexing 101. Let's use a file system to index the data. And before I get a lot of weird looks, I'm gonna punt on that for a second, and I'm gonna finish through this list of operations before I get into this indexing operation. But yeah, we use the file system. And on the right-hand side, aggregation, transformation, logic, we just use Python. Python, all developers are comfortable with Python. You essentially think of you're querying a database, and you get data back, a stream of log lines. And we've completely abstracted away. We created some APIs so that we write a lot of our services. We use our APIs, and we allow developers to subscribe to any lines. They can use our APIs to pull the data and stream through it. We provide Spark clusters so that you can use PySpark to submit your jobs and process through these log lines as well. And on the visualization, we use Grafana, InfluxDB, alerting to plug into a lot of the different services that we might want to alert through. We alert through some very, very high-level events, very few, but we might alert through email. For repeated bugs, we alert through that through Jira, because we use Jira as our bug tracking system. So that's actually been really useful for our developers when they see they have a bug that is filed to them. Somebody goes and writes what we call a signature. A signature is essentially one of these patterns that you're subscribing to. And that pattern could be one log line, or can be essentially a list of log lines with certain logic attached to them, like ands and ors and time windows. And when that event happens, after the post-processing step, we can now tag that onto a Jira and say, hey, your bug has hit 1,000 different failures. You should really look at this. So you're affecting a lot of people, right? Because you're not just affecting the test that is happening, but people are constantly checking out the code and making their own changes, and now their tests are failing because of your bug, so they cannot differentiate between your bug and their bug. So that's kind of a problem there. So engineering productivity is on top of mind. And the part that I'm going to focus on next is the FlashArray, right? Because this is kind of interesting and weird, because we do indexing, which is essentially a database operation on a file system. So how do we do that? We use the file system directory structure to encode metadata. If you think about it, a file system, it is sort of like tagging of metadata into the files. So the raw data, which is the producer, is being produced by our syslog, is being stored in this format: host, year, month, day, and the flat files. The flat files will encode the name of the software process and the hour that is being generated on. So the consumer of all of this data is the refilter step, or a lot of times a custom look back. Somebody just wants to go back through time and look back through the last week of all logs for maybe a given host, or maybe for all hosts, right? Everyone is free to look through that data however they want. But it is a little limited in terms of the kind of slicing and dicing of data that you can do, right? You can only slice it by host or time, essentially. Or maybe software process, because that's encoded in the flat files. But for all of the use cases that we have, that's plenty. Now, the raw data was the easy part. The index data is now a little bit more interesting, because we take a different slicing and dicing of that data, and we use pattern as the main thing. Because if you think about it, the configuration input that is going into this system is a list of patterns, a list of lines that you're subscribing to. Now, if you have, for example, an alerting event that takes multiple of these lines with logic attached to them, the consumer is going to query the index for all of these lines and then do the operations after. But now you're not searching through all of the data. You essentially have a consumer-producer model of only the lines that you care about within given time periods, because data is also essentially has been sliced by hour. So it gives you a much, much smaller window of data to look for any one given event that you care about. And there's also the host, so that helps you correlate across the same host. The producer of this index data is Spark streaming, and the consumer is Python, the Python services. Again, APIs that we've created so you can query this data. So writing was honestly fairly straightforward. A lot of people think of file systems, or essentially storage, as really slow. But you don't need to essentially wait for ACKs when you're writing data. If you trust that your storage is reliable and available, you can just asynchronously, constantly keep writing to storage. And obviously, you're keeping track when ACKs are coming back. But because of the asynchronicity of the process, it allows you to keep constantly essentially consume and process all of the data as it is being generated. So writing was not complicated, but the querying part was now where we got into some interesting problems. So querying is, you're finding the data, where is my data, and then you have to load it. Very simple process, right? So in our FlashArray product, we use our NFS protocol, and we have sort of changed the NFS world in the fact that everyone thinks that NFS is really, really slow. We've created an NFS appliance that essentially has under 1 millisecond latency. And you might think that's really fast, right? And it is, but when you're querying a directory structure that may have 1 million files for an hour, and the Linux NFS client kernel, when you do an operation like an ls-alr, it may come back in like 10 minutes, maybe 30 minutes, depending on how many files you have. So even under 1 millisecond latency for each of the operations that you have to an NFS file system, ls-alr could take forever. And we obviously cannot afford to have like 10-minute queries. So where is the bottleneck? The bottleneck is actually not on the NFS server, it's on the NFS clients. The clients are actually doing sequential listing and are going through a directory structure and going through all of its children and waiting for the response back before they issue the next request. So this 1 millisecond latency, you multiply by 1 million files, and that's how you get the latency of your ls-alr to take forever. So the solution is to skip the kernel. Say, lucky for us, somebody has already built a user-level NFS library. So it's called libnfs. You can look it up. It's open source. It's written in C++. There are Python bindings for it, so you can easily import it into whatever package you have. And we essentially use libnfs to create our own parallelized version of a directory, essentially tree discovery. We can parallelize this as many times as, with as many threads as we want. And in our case, we use 32 threads as the default, and we're 1,000x faster because now we don't have to wait, and there's no serialization. So now you can really take advantage of the 1 millisecond latency of a given operation, and by adding parallelization, your whole query can be a lot faster. So that's just helping to find the data, right? Because we use, again, the file system, you can now find where the files are that my data may be. And then the reading part, all we had to do was do some buffering. For a 1 millisecond latency for a half a megabyte operation of a read from storage, it's still fairly small, but when you're reading, again, hundreds of files, it adds up. So all you gotta do is create buffering, right? So you wanna hide the latency away. All of the operations in log analysis, you have to think and design them with throughput in mind, not with latency in mind, because you really wanna be able to keep up with the high load, not necessarily with make your queries like a millisecond. I care that my queries come back in half a second. That's plenty for us, for our use case at least. But that query may still bring up 10 gigabytes of data into a single host. So how do I do that without paying for the latency cost? You buffer. And this is a common operation. It happens also in you think of training jobs for AI. They're loading large amounts of data into GPU. How do they do that? They have CPUs attached to them that are bringing in the data ahead of time so that the GPUs is already in memory and they can consume it freely. We took the same concept and we did that here. Now, in terms of how does this look like from the number of hosts and all of our services that we have. Our full pipeline today, as promised, we did grow. We have a lot more hosts now. We have over 300 FlashArrays, 1,000 of these clients, and 2,500 of these VMs. By the end of this year, we're going to have 5,000 of these VMs. From 70,000 tests, we're now running 120,000 tests per day. And it's not just the number of tests that have grown, but also the number of log sources that we are ingesting more. Originally, we were only ingesting the stuff that was going through syslog. We've created our own little libraries and so that you can essentially ingest almost any log sources that are being streamed into your local disk. So we have our syslog servers. We have this for compaction. The syslog servers are actually 4 cores. They're hard to scale up, so we have to scale them out. And we have 24 of them, and we do our own load balancing across the syslog servers. The syslog servers, as I mentioned, are writing all of the data to the FlashArray. Additionally, they're teeing all of that data to the Kafka server, and it's 72 terabytes per day. This is where data explodes. 24 terabytes of data per day is being generated from the log sources on the left. And here is where we're tagging it with even more metadata. So it's not just host and time. Now we're using metadata like what job were you running, what Jenkins branch were you running, what are the node labels, what is the SHA of the code that you are running. A lot of details that can help us essentially slice and dice the data in different ways. So data grows by about 3x here, from 24 terabytes to 72 terabytes. A Kafka cluster, 12 core VMs, containers. Everything's containerized in this environment. And then Kafka is just there to serve those 72 terabytes over to a Spark streaming cluster. On the right, if you're familiar with Spark streaming, the UI, it shows you somewhere between 1.5 to 2 million events per second, based on the different times and based on whatever tests are running. Certain tests generate more or less logs than others, and you see just patterns that are happening there. This Spark streaming job obviously runs 24/7. It's been running in production for about 10 months. It has grown when we started from about 500,000 records per second to about 2 million, so it's already 4x. And by the end of the year, we should be about 4 to 4.5 million events per second. And so far, it's been so easy to scale, right? Like if you have more data, you just need to add more syslog servers, more Kafka nodes, more Spark nodes, and off you go. All of these, we've tried to pick the technologies that are have the fewest number of dependencies in terms of scalability. This data, there's about 800 gigabytes. That is the index data. That's how much data we're actually using today, whether we're making it searchable on the right-hand side, or we're transforming an ETL in it, or we're using it to alert and do these fingerprints to identify actual root causes of problems. And all of that's done in a bunch of servers that are just running Python, and they're constantly consuming through Kafka. So these 800 gigs are actually going to the index, and a lot of these lines are sending notifications through Kafka for the services as well. So the services are not necessarily just consuming from the index. They're a lot of times consuming from a Kafka queue saying, hey, do I have work to do? And then they go query the index, which is in the file system. And there's about 800 gigabytes of data. The output, now the business case and why we built this, right? The kind of alerts that we have is like, hey, this test has not even finished, but I know that it's going to fail because of the root cause that somebody identified yesterday in this other test, and it's attached to a certain JIRA, so I can add 1 to this hit count of this JIRA, right? So now a lot of our productivity has gone up because now you know exactly what are the tests that are causing the largest number of failures in our CI/CD environment, right? Now management can say, man, this feature is going, so far as we thought, like it's on time. There's a lot of bugs, and they're now not just affecting this feature, they're affecting everyone else. Because if you think about it, you have 100 developers, one developer adds a bug, everyone else is getting slowed down because everyone else is going to fail their tests on that bug. And they won't be able to tell if their code is the cause of that bug or not. Now we can. We can tell you with these signatures that test that you ran is because of somebody else's bug, and it's not your bug, and therefore you can keep going. Right? So you can still merge this to our master branch or to your feature branch and be comfortable that these fail for a known reason. Obviously, performance regressions, infrastructure failures, we can capture those kind of scenarios. And as we're going forward, we're going to be adding more and more services from this data. Searchability, right? I mentioned trying to capture all the warnings so that you can make those quickly searchable. We're thinking about using, obviously, Elasticsearch for that, but now it's a much smaller footprint of data. And on the refilter step now, so this is the stuff on the top was our streaming pipeline. On the refilter step, we have a second Spark cluster that when somebody goes and adds a signature, for example, and again, these signatures are these patterns that identify, match log lines and logic to bugs. When somebody goes and adds a signature, what we have to do is now go back in time for at least 1 or 2, 3 days, because there are failures in the past that are probably for the same reason. And we also don't want you to go spend time, right? Because the streaming pipeline is going to capture everything else in the future, but not the stuff in the past. So we go load about 3 days worth of data, and we process all of that and look for the same patterns so that we can now automatically triage stuff in the past. And that's what this little cluster is doing. And on the performance stuff, when we now understand that there's a performance regression. So the ETL stuff, the data that gets ETL automatically is the very, very high level data. So essentially the performance metrics at a high level. But now you need to understand, okay, so why did my performance regress? And in order to be able to do that, you need to dig down much, much deeper. And we have those metrics. Metrics in terms of interaction between the different software components inside our product, or metrics of the hardware inside our product. But now we want to go process those in detail. So now you can issue a particular job that will go and extract an ETL or that data when you need it. Right? So you don't constantly process all the data and pay the cost of processing all the data all the time, just when you need it. So this pipeline here will give you like easy to read graphs, and we have Grafana, essentially dashboards that we export and people can bring in and do their own analysis there.
Question. Why 3 days?
Why 3 days? Because after 3 days, honestly, nobody cares. I mean, if you have a test failure that was more than 3 days ago, nobody's going to look at it. If it has not been looked at, nobody's going to look at it. Right? That's the reality of things. We have a triage team today. The triage team has 3 people, not 20. Their job is to get to 100% triage of all failures. Right? There are days that they can get there. There are days that they cannot. Right? Because it's the reality of things. Sometimes you have a lot of problems, infrastructure problems, testing infrastructure problems, and you can't do that. But with this system, it's the first time they've been able to even get there, because it's not now a constraint of their time, but it's a constraint of like how quickly can they write these signatures, and so that we can get to that 100% triage. So all of these applications, as I mentioned, are deployed in Docker. We don't use Kubernetes. We use Nomad for orchestration of all of our containers. The main reason for that is just historical reasons. We've used Nomad inside the company for about let's say 6 years already. So we already had made an investment in sort of our developer tools team to essentially operationalize Nomad. So we've done that. At some point in the future, we might want to switch to Kubernetes because it does better resource management. But in order to get this off the ground, it just worked flawlessly on the Nomad side. We monitor all of this infrastructure. You obviously, just like the code that we're trying to monitor, we have bugs. We introduce bugs ourselves. So we need to understand when stuff backs up, where does it back up, why is it backing up? So we have to extract metrics from all of these applications into a monitoring system. We use Prometheus for that. We're starting to do essentially a test drive with Thanos now because we want to not just use 7 days worth of data, which is what we could get in Prometheus, but now we want to start looking at longer analysis of our pipeline. And Thanos allows you to export that data into an S3 interface. And hey, guess what? Our product also does that, so we want to use that and leverage that as well. So, we're going to be doing Thanos for that, for the aggregation of the metrics across all of our different services and all of our different hosts. So we can, we export CPU, memory, network from all of our services, and additionally a lot of like service defined metrics, like how many log lines am I processing in this last second per host? What's the average size of log lines? How many are getting filtered, and those kind of details. So the takeaways from building these pipelines, right, is index only what you need, and obviously store the rest. This is a pattern that is actually fairly common if you're building these kind of applications in the cloud. The cloud services that you may be using for that are doing this for you. But if you're building this yourself, whether it's because you're doing it on-prem or because you have limitations of the kind of technologies that you're using, think about this concept. Store it in a layer that actually scales in terms of throughput, because if you store it in a storage layer that will not scale throughput-wise, it's essentially unreadable data. You're never going to be able to do anything with it. So why are you even storing it, right? So think about data in two ways. Are you ever going to touch it, or are you not? Because if you're not, then it doesn't. Why are you even storing it, right? If you cannot read it fast enough, why are you even storing it? So throughput matters in big data. Optimize for throughput and not latency. Again, we're not a high speed trading firm. We don't care about millisecond actions or microsecond actions from one of our events. Log lines can 1 second, 5 second SLAs are plenty good, because our humans generally on the other side that are taking action from those. So optimize all your services for throughput and not for latency. So parallelization, buffering pipelines, input pipelines, those are great concepts that you should implement for your systems. And the last one is, and I'm sure you've heard this all over. I've heard this concept at least 5 times in the last day, from the Netflix talk, from a bunch of other talks about disaggregation of compute and storage, right? A lot of people in my team have past lives in the Hadoop ecosystem, and that comes with a lot of pain because of the aggregation of compute and storage. So when you want to scale different systems to throw more compute at a problem, but not necessarily more storage, or you just need more storage to store your data for longer periods, but you don't need more compute for the processing that is coming in, that's really difficult to do in Hadoop. It's really difficult to do multi-tenancy. It's doable, but it's a headache. So a headache that nobody should have to deal with. And if you disaggregate everything, so you think of your compute layer as just that, racks of servers, or if you're in AWS, EC2 instances, and try to use as much as you can of those EC2 instances for the compute and S3 for the storage, because that will allow you to scale each one of them independently. So think of each of your subsystems as scalable pieces, so that they should be able to process the full load of all of your log lines or whatever it is that you're processing. Thank you very much. I'll be happy to take any questions.
You want also microphone, or you can? Okay.
Hi, my name is Maulin. I have 2 questions, but I'll ask simpler one first. So from the diagram, I could see that you have 1 Kafka cluster. Is that the case?
Yep.
Okay. And the second question is, how do you translate your logs to how do you map the log entries to bug?
Mm-hmm. So there's a human that is doing that, right? So the human that is looking at a failure that has not been triaged is essentially doing the linking between a failure and a root cause. And how are they doing that? Through logs.
I
So
see.
they mark line A plus line B plus line C in a 60-second window are equal to this bug.
I see. Okay, that makes
So that's
sense.
input, configuration input to our system.
So,
Spark layer takes that configuration as input and is doing the filtering. Now the services on the right-hand side are the ones that are doing the logic of aggregating the different lines that you've subscribed.
So you are saying the story in the last report, right? So do you refresh that every day?
We refresh that. Like, so you mean the configuration of all of the patterns?
The data, every day data flow in, right?
Mm-hmm.
Then you index it.
Yeah.
So data, some of data will be the same, right? So how you can do it? You refresh constantly.
I mean, the index constantly grows. We have data fall out of an index after about a couple of weeks, but for some of them we choose to keep them for years because developers require that.
So the index will be like the timestamp is in the index.
Yes.
This is the key.
Yep.
Okay.
Mm-hmm.
Hi. Yeah, just a few really quick questions. So do you run this on-prem or in cloud? Maybe I missed that.
Yeah, on-prem.
All on-prem.
Everything is on-prem.
And for Kafka and Spark, do you also use Nomad to run those?
Yeah.
Yes.
Everything runs on Nomad.
Cool. And final question. For Spark, because you basically have your custom storage layer, right?
Yes.
For Spark, does it look like a local file system? Or
It's
you have
NFS,
like
so it's network file system. So you mount the file system and you just write to it, like as if it were a local file system.
All right. So from Spark perspective, it's like local files.
Yeah.
Pretty much. Okay. Thanks.
We actually use the network file system as backend for Kafka as well. So even the Kafka nodes don't have any local storage. So we have to do persistent containers, right?
Two questions. First one was, is there any compression in this, or are you?
Great question. So our storage layer does compression for you. So we do not compress the data at all. We have LCO compression that it happens as you're writing. So you already get, for log data, you get about a 5-to-1 ratio of compression. And then as data is aged out and you don't touch it, we have deep compression, and you should get about 10-to-1 for log data.
And then the other question, you have up there you're using InfluxDB, but you also mentioned Prometheus.
Mm-hmm.
Why two? Are they using different things, or what's going on there?
There's no particular reason, to be honest with you. We like to try out every new technology that comes out. So we've tried out at least 20. Sometimes some of them stick, and you just keep going with the flow, and sometimes they don't. The reason why we chose InfluxDB for the performance data was at the time, Thanos did not exist. So Prometheus couldn't scale past a certain size because it wouldn't scale out. But now that Thanos exists, we could think about replacing InfluxDB for Prometheus or using InfluxDB for the other one. On the other hand, InfluxDB, you have to pay when you want to scale out. And we didn't necessarily want to pay. So there's that. It's free for a single node, and for the stuff that we wanted to do was plenty.
So you mentioned that for Spark, all your data is read from NFS.
Mm-hmm.
So your scalability is really impacted by actually how much NFS can process it parallelly, your I/O.
Exactly.
Right?
You're exactly
So you
right.
cannot just scale in Spark world. You're going to get always bottlenecked by the NFS.
Yes, and that's exactly why we did this. Our storage platform here scales to essentially massive amounts of parallelism. We are serving an NFS server from thousands of hosts, and with our current platform, we can serve up to 75 gigabytes a second of read throughput. So you do have to have a storage layer that scales in throughput, otherwise none of this works. And that's why if you're doing this in the cloud, you should use S3, because S3 also has similar scalability throughput-wise. But S3 also has much worse latency, but you can still hide some of that away.
Thank you all, and please thank Ivan for a great talk, and I really enjoyed. Please.
Thank you.